Today we are going to learn about mastering indexing for efficient database queries. We will explore how to implement and manage indexes effectively to optimize database performance and query speed. Welcome to our video on mastering indexing for efficient database queries. In this session, we'll explore the vital role of indexing in databases. Indexing acts like a roadmap, guiding your queries to the information they need quickly and efficiently. Especially in large datasets, indexes serve as a critical tool for optimizing performance, enhancing query speed, and ensuring that your database operates at peak efficiency. By the end of this video, you'll have a solid understanding of how to implement and manage indexes to improve your database's performance.
Let's start by understanding what indexing really is. Indexing in databases is akin to an index in a book. It's a data structure that improves the speed of data retrieval operations on a database table at the cost of additional writes and storage space. The primary purpose of an index is to provide a mechanism for quick access to rows in a table, similar to how a book index helps you find a specific topic quickly without flipping through every page. Internally, indexes are built using a variety of data structures like B-trees or hash tables, which organize the data in a way that makes it faster to search. Without indexes, a database must scan the entire table to find the relevant data, which can be slow and inefficient as the size of the table grows. By the end of this video segment, you'll appreciate how indexes make databases more efficient and effective.
Indexes come in various forms, each suited for different scenarios. Let's delve into primary and secondary indexes first. A primary index is typically unique and is associated with the unique identifier of a table, like a primary key. Secondary indexes, on the other hand, are not unique and can be created on any column to enhance query performance. Then, we have unique indexes which ensure that the values in the index key are unique across the dataset, preventing duplicates. Non-unique indexes allow for duplicate values. Next, let's discuss clustered and non-clustered indexes. A clustered index sorts and stores the data rows of the table based on the index key, effectively determining the physical order. There can only be one clustered index per table, as the data rows themselves can only be sorted in one order. Non-clustered indexes, however, have a separate structure that references the data rows and can be many per table. Choosing the right type of index is crucial, as it directly impacts performance, storage, and maintenance. Each type has its use cases, from ensuring data integrity with unique indexes to optimizing read-heavy operations with secondary indexes.
Indexes significantly enhance database query performance. They reduce the time it takes to retrieve data by allowing the database engine to locate the required rows quickly without scanning the entire table. For example, if you have a query that searches for a specific record, an index can reduce the search operation from a full table scan to a much smaller subset of the data. This is akin to finding a specific word in a dictionary rather than reading every page of a book. Indexes also facilitate sorting and filtering operations, making them much faster and more efficient. When dealing with complex queries involving joins, indexes on the join columns can dramatically speed up the execution time. When writing SQL queries, the database engine uses the available indexes to optimize the query execution plan, selecting the best path to retrieve the needed data. By the end of this section, you'll understand how vital indexes are to making your queries run faster and more efficiently.
Designing effective indexing strategies is key to optimizing database performance. For read-heavy workloads, it's crucial to identify the queries that are executed frequently and ensure that indexes are available to speed them up. Compound indexes, which consist of multiple columns, are useful for queries that filter or sort on multiple columns simultaneously. These can greatly enhance the performance of such queries by reducing the need for the database to fetch additional rows. Covering indexes are another powerful strategy, allowing queries to be resolved entirely from the index itself without accessing the table, which can save significant time. When designing indexes, it's important to be selective about which columns to index. Indexing every column is inefficient and can slow down write operations and increase storage requirements. Avoiding over-indexing is crucial, as it can lead to increased maintenance overhead and reduced performance for write-heavy workloads. By understanding these strategies, you can design indexes that strike a balance between read and write performance, maintaining an efficient and responsive database.
While indexes are invaluable for read-heavy operations, they can negatively impact write performance. Maintaining indexes requires additional I/O operations during insert, update, and delete transactions, which can slow down these operations. This is because each change to the index data requires the index to be updated, adding overhead. There's a trade-off between optimizing for fast reads and maintaining efficient writes. To balance this, it's essential to carefully choose which indexes to implement. Strategies for minimizing write overhead include indexing only the most essential columns and considering partial or filtered indexes for specific subsets of data. Monitoring your database's write operations and adjusting indexes as needed can help maintain an optimal balance. Understanding these trade-offs and strategies will enable you to manage your database's performance effectively without compromising on write speed. Maintaining indexes is crucial for sustaining database performance. Over time, indexes can become fragmented, leading to inefficient data retrieval. Regular maintenance, such as rebuilding or reorganizing indexes, is necessary to keep them in optimal condition. Rebuilding an index drops and recreates it, which is effective for severely fragmented indexes, while reorganizing is less intrusive and simply defragments the index pages. Monitoring index fragmentation levels and performance metrics helps determine when maintenance is needed. Automating index management tasks using database management tools can save time and reduce manual workload. Adhering to best practices, such as scheduling maintenance during low usage periods and prioritizing critical indexes, ensures that your database remains responsive and efficient. By the end of this section, you'll be equipped to maintain healthy indexes and sustain optimal database performance. Analyzing the effectiveness of your indexes is crucial for optimizing database performance. Database management tools provide insights into how indexes are being used and their impact on query performance. These tools can measure index usage by tracking how often an index is accessed and identifying indexes that are rarely or never used, which can potentially be removed to save resources. Analyzing query performance with tools like query execution plans can reveal bottlenecks and areas where indexes can be optimized. By tuning indexes based on this analysis, you can ensure that they are efficiently supporting your database's workload. Leveraging these tools and techniques will empower you to make informed decisions about index management and optimization. Understanding the benefits of indexing in real-world scenarios can solidify your knowledge. Consider a case study where a company implemented strategic indexing and saw a significant improvement in query speed, reducing execution times from minutes to mere seconds. This not only improved user satisfaction but also reduced server load, which in turn lowered resource usage and costs. Another example involves an application where indexing led to noticeable performance gains, allowing it to handle more concurrent users and scale more effectively. These real-world examples highlight the transformative impact that well-designed indexing strategies can have on database and application performance. By learning from these examples, you can apply similar strategies to your own databases, achieving scalability and efficiency.
As we conclude our exploration of database indexing, let's recap the key concepts. We've covered the fundamentals of indexing, different types and their use cases, how indexing can transform query performance, and strategies for effective index design and maintenance. Remember, ongoing index management is crucial for sustained performance. We encourage you to implement the strategies you've learned today to optimize your databases. For those interested in diving deeper, there are numerous resources available for further learning. Don't forget to subscribe to our channel for more educational content on database management and optimization. Thank you for joining us, and happy indexing!